For topic 2, we're going to look at multiplying the sum and difference of two terms. Okay, so a new definition. We do have the idea of conjugates. Okay, so conjugates in algebra are binomials that have the same terms, but in one binomial you add, in the second binomial you subtract. Okay, so think like a plus b, a minus b. Okay, so if you have a binomial of the form a plus b, the conjugate is a minus b. So again, I wrote that out up here, but notice we have a and b in the same order. All right, we just change from addition to subtraction. So one term you're going to add those two terms, or one binomial you're going to add those two terms, and the second binomial you're going to subtract those two terms. Or the first one you could subtract, the second one you could add. It doesn't matter which one you add or subtract, just know you're going to have two terms, you add them, you subtract them. Okay, the important property of conjugates is that when multiplied together, the result is the difference of squares, and this is what's going to come up in a future chapter when we talk about factoring. Okay, so we have this idea of the difference of squares that, again, you're not going to necessarily say the difference of squares now, but the difference of squares is definitely going to come up in the future. Okay, so remember the FOIL method. We have, if you have a plus b times a minus b, so remember those are our conjugate pairs, you take the first terms, that gives you a squared. You take the outer terms, that gives you negative a times b. You take the inner terms, that gives you b times a or a times b. And then you take the last terms, which gives you negative b squared. Well, notice what happens with those middle terms. When you multiply conjugates, those middle terms basically just cancel out. They become zero. So essentially, you can just take your first terms and your last terms when you're dealing with conjugate pairs. Now, this only works when you're dealing with conjugate pairs, okay? So instead of multiplying using the full FOIL method, the special product formula is just multiply your first terms, multiply your last terms, because we know that those middle terms are always going to cancel out to become a zero, okay? Now, I'll show you the first couple of examples using the FOIL method just to prove to you that those middle terms are going to cancel out. And then for the last one, we'll just do the special product formula. Okay, so example 2 here says find each product, write the answer in standard form. So like I said, I'm going to show you the FOIL method for the first two examples just to make sure you believe that those middle terms cancel. And then for this last one, we'll use the special product formula. Okay, so if we were to FOIL, we have the first terms. We're going to apply the product rule, x times x. We keep the base and we add the exponents. So we're just going to get x squared. The outer terms would be x times 2. So x times 2 is just 2x. We now want to look at the inner terms. That's going to be negative 2 times x. So negative 2 times x is negative 2x or minus 2x. And then finally, we want to look at the last terms, which would be negative 2 times positive 2, which is going to be minus 4. Now, what do you notice here about these middle terms? Well, I have 2x minus 2x. That cancels out to just become 0. And when we add in a 0, nothing happens. So at the end of the day, we're left with x squared minus 4. So you're always going to end up with the first term squared minus the second term squared, basically. Okay? So there you have it. And notice right here, this is the difference of perfect squares. You know you have perfect squares with variables if the exponent is divisible by 2. So we have x squared, 2 is divisible by 2, so x squared is a perfect square. And then we're subtracting, that means difference. And then 4 is also a perfect square. Okay, a perfect square being a number that has a whole number square root or a nice pretty square root. Okay, now for the middle example, we have 3x plus 4 times 3x minus 4, definitely conjugate pairs. We're taking 3x and 4, we're adding, and then we're subtracting. Okay, so again, we're going to do the FOIL method just to prove to ourselves that those middle terms really do cancel. So 3x times 3x, those are the first terms, that's 9. And then we apply the product rule, x times x, we keep the x and add the exponents, so 9x squared. And then we take the outer terms, so that's 3x times negative 4. So 3 times negative 4 is negative 12, and then we just keep the x. We take the inner terms, which is 4 times 3x. 3 times 4 is 12, and then we just keep the x. And then finally, we do the last terms. 4 times negative 4 is negative 16. Notice, just like in the previous example, those middle terms, they cancel out to become a 0, okay? And we're left with 9x squared minus 16. So this is our final answer, and yet again, you can see here that we have the difference of perfect squares. So we're subtracting two terms. The first term is a perfect square. We know that 9 is a perfect square because its square root is 3. X squared is a perfect square because the exponent is divisible by 2. And then 16 is also a perfect square. Its square root is 4. And we're again subtracting. So we know that this method really does work. We end up, our final product is the difference of squares, and those middle terms are going to cancel out using the FOIL method. Okay? So for this one, let's go ahead. Part C, let's use the special product formula, which is right here. So the special product formula is basically a shortcut. It tells us that in this special case where we're multiplying conjugates, we can just multiply the first terms, multiply the second terms, and then we're done, okay? So x squared times x squared, we apply the product rule. We keep the base, we add the exponents, and then we can look at negative 5x times positive 5x. Well, negative 5 times positive 5 is negative 25. And then x times x is x squared. So, yet again, we have the difference of perfect squares. So this right here is definitely a difference. We're subtracting. That's supposed to be an F. Pretend. I can't. That looks so ugly. Difference of perfect squares. So we know that x to the fourth is a perfect square because 4 is divisible by 2. 25 is a perfect square. Its square root is 5. So that's how you know you've got a perfect square if you have that nice whole number or natural number square root. And then x squared is a perfect square because its exponent is also divisible by 2. And of course, we're subtracting. So you can see that when you multiply conjugate pairs, number one, if you were to do the FOIL method, the middle terms cancel out to become 0. So you can take those special product shortcut where you just multiply the first and last terms. The result is always going to be the difference of perfect squares.